Okay, so we've seen that NNIs are local transformations of a tree, and they consist in swapping two subtrees around a branch. And obviously you have two NNI moves per branch, as we just saw here. And how many internal branch? You have 2n minus 3 branches in total in an unrooted tree. So n minus 3 internal branches. So you have 2n minus 6 possible NNI moves from a single tree. So it's still a large number of possible moves, but it's not completely at random. You know, if you fix as a constraint in your random walk that you move from one tree to another using NNI moves, then it's already a significant constraint. The next transformation we're going to see is called SPR, subtree pruning and regrafting. So it's a less local rearrangement, pruning a subtree, so cutting it from the rest of the tree, and then regrafting it onto any of the branches of the tree. So if we see on this example here, this is the original tree. If I decide that I'm going to do the SPR involving cutting this branch here, now I go down here and I'm left with this thing and this original tree, like this subtree that I cut and the original tree where we merged these two branches from D2K. Okay, so here we have merged these two. Right, now regrafting is going to mean that I'm going to regraft this subtree from on this point, but I have many different options to regraft it on this original tree, right? So I can choose to regraft it on this branch, on that branch, on this other one, on this one, etc. Okay? Not on this one, because if I regraft on this one, I just obtain what I had earlier. So with a star here, and this illustration is thanks to Joe Felsenstein. I mention it in the next. I mention him in the next slide, but not here. It's sorry, I forgot. So if I branch here, if I regraft here, you see that what I get is this topology, right? So from this original tree into this tree, I've modified the topology by one SPR, okay? So SPR is a more complex move than NNI, okay? We can show that NNI is just one type of SPR move, but there are some SPR moves that are not NNIs, okay? So NNIs are included into SPRs. Right, so pruning and regrafting. The next one we are going to see, the next transformation, elementary transformation, is slightly more complex. It's very close to the SPR transformation, but the difference is that whereas before in SPR, when you cut one tree, you regraft using, you have this like this original tree and this part that you cut, and you're going to regraft the part that you cut, so it's a bit asymmetric. You're going to regraft the part you cut onto another branch of the original tree. Okay, it's asymmetric. With tree bisection and reconnection, you first bisect, and after bisection you have two trees. Okay, two trees. Like here, we cut here, we break a branch, we separate the two subtrees, then we have two subtrees. Now we're going to have many more options to reform a tree than we're given just by SPR, because now we're going to merge these two by, in a way, identifying one branch of the one tree to another branch on the other tree, and say, okay, we're going to connect the two trees from these points. So So here, for instance, if I identify this branch here of this tree with this branch here of that other tree, I'm going to merge these two and create, to preserve the fact that the tree must be a binary tree, I'm going to create a branch here, but here I had deleted one, so at the end we have the same number of branches. I'm going to create my branch, and then this is my tree. And it's still a binary tree, okay? You can check that every internal node is connected to 3 different neighbors, right? So it's a TBR is a tree rearrangement where we perform bisection, cut the tree into 2 subtrees, and then reconnect by choosing independently one point in the one tree, one other point in the other tree, and then identify them or connect them with a branch, with the additional branch that is here represented in red. Okay? So SPR moves that we saw earlier are simpler. Okay? They form a subset of TBR moves because the constraint in SPR moves is that you would reconnect identifying this point. Remember here, SPR moves, if you take this example here, they in a way remember that this subtree was cut here where my mouse pointer is. Okay? It was cut between J and H. Between J and H, it was cut here. Okay? We had one extra edge here. So it would be identifying this branch with any point here. All right? But with TBR, you have the choice to reconnect or regraft on another point of the thing that you cut. Okay, so it's a more complex transformation. Every NNI move is an SPR move. Every SPR move is a TBR move. But you cannot go the other way around making the same statements. Okay, there are TBR moves that are not SPR moves, and there are SPR moves that are not NNI moves. So there is more complexity in an operation of tree bisection and reconnection. So these 3 families of moves, these 3 types of moves that we've seen, are used in phylogenetic inference software to browse the space of all possible phylogenies, performing alterations from one tree to another one. And why do we do this? Why do we perform such a random walk in the space of trees by alterating an existing tree? We do this because in the process where we're going to calculate the costs that we want to optimize for the new tree, we're going to reuse parts of the costs of that we calculated in the previous tree. So from the viewpoint of computational efficiency, it's a good thing to explore this space of possible topologies, hopping from one tree to another, using these kind of elementary transformations that are local or semi-local. Semi-local because you still preserve parts of the tree, the original tree. Like for instance here, this you don't preserve so much, but for instance this subtree DAEK here was preserved. Okay, CDAEK, or this subtree was preserved here. Well, let's talk about the likelihood of a tree now. Okay, so these 3 types of different moves are used. There are methods used to transform trees in the framework of a heuristic search into the space of trees. Sorry. So far we saw distance matrix methods. So distance matrix methods are a bit separate from the rest, because in distance matrix methods, you remember that we do not explore the space of trees. Okay, we just build one tree. We never go back to undo what we've done. It's greedy methods. They are not exploring the space of trees. They are automatically building one tree, right? We saw also maximum parsimony methods, and I showed you how to calculate the parsimony costs given a tree and a labeling on the leaves, and it was a Fitch algorithm. But when you are in the framework of maximum parsimony, you still have to explore the space of trees. Okay, Fitch algorithm helps you perform the calculations on one given tree, but you'll have to explore the sets of trees to try and find the tree that minimizes your parsimony costs. Here, with the likelihood of a tree, we're going to introduce likelihood methods, maximum likelihood methods, and it will be another criterion that you're going to optimize. But be it in maximum parsimony or in maximum likelihood, you still have to explore different topologies, a space made of different topologies. And so that's where your NNI, SPR, and TBR moves are used in your phylogenetic inference softwares. So the definition of a likelihood, I already gave it to some of you who asked questions about it in a previous session on MCOM for VULA. Given some observed data D, the likelihood, and in French likelihood is translated into vraisemblance. So the likelihood of a model M is the probability that the observations that we have, so the data, observations or data D are synonymous, the probability that these observations originate from that model. And this model is seen as a generative model, so a model that can produce what you see as aligned characters. For instance, if you take the example of phylogenetics, aligned characters in a given site in an alignment. This likelihood is given by this formula. The likelihood of a model is the probability of the data knowing the model. Okay, probability of the data conditional on the model. So in phylogenetics, the observations D are the traits corresponding to the taxa on the leaves, for instance, an alignment of nucleotides or amino acid residues. And the model M is a combination of three things. Okay, so it's first a tree topology. So topology meaning without considering the branch length, the way nodes are connected to each other. So this tree, a cyclic graph, but without weights on the edges. The corresponding branch length is the second component of the model, and the third component, is the evolutionary substitution model. And usually, most often, it's given by the specification of a matrix Q of instantaneous substitution rates. And remember, we saw this kind of matrix when we talked about JC69, the Jukes-Cantor model for substitutions in nucleotides. So, and this evolutionary substitution model is believed to be acting on the branches of the tree. Okay, so these three components form the model, and we're going to calculate what is the probability of what we see on the leaves of the phylogeny, given that model, given this model as a given. Okay, so the probability conditional on the model. Let's have a break now.